Hello, I'm Doug Montgomery, your instructor for the Design of Experiments MOOC. I'd like to welcome you back to our September Fireside Chat. For those of you that are newer to the MOOC and our Coursera courses, this monthly Fireside Chat is something that we've been doing from the very beginning. And we have a guest speaker every Fireside Chat. And we explore specific topics and applications of experimental design. And the guest always gives I think, a really super interesting talk about some either specific technique or application that they've been involved in. We always leave some time at the end of the guest presentation for some Q&A. And this is a great time for you to ask questions. And they can either be about the content of the Coursera courses or something specific to a situation that you're encountering, or maybe something about the talk that our guest is going to give. So really anything you want to ask would be great. And we always post these Fireside Chat recordings to the courses. So they're in the resources tab of your course. A couple of just quick reminders. Please continue to keep your microphones muted, your cameras off during the session so we don't have any extraneous noise. And if you want to submit a question to either me or the guest, you can do that using the chat function on the Zoom menu. You don't need to wait until the Q&A starts to do this. You can put that question in at any point during the session. And if we don't get the question answered during this time, we will respond to it in Coursera for those people that are enrolled in the course. Our guest today is Katie Brickey, who is a statistician at Pfizer, one of our premier biopharmaceutical companies. Prior to joining Pfizer, she worked for 7 years as a statistician at Eastman, a materials innovation company that produces a lot of the products that we see in items that we use every day. And she just told me that this is her 1-year anniversary at Pfizer. So congratulations on achieving a 1-year anniversary. She very frequently uses statistical methods like design of experiments, statistical process control, other modeling techniques in her everyday work. And she serves currently as the chair-elect for the American Society for Quality's Chemical and Process Industries Division. Big responsibility there, Katie. And she holds a master's degree in statistics from Virginia Tech. So, Katie, I really appreciate your taking time out of your really busy day to give this presentation, and the floor is yours.
Thank you so much, Doug. I appreciate it. It's great to be here and talk to you all today. Am I sharing my screen? Can you see it okay?
Yep.
Okay, perfect. Just wanted to check. So today I will share with you about a case study, and the title of the presentation is called A Staggered Level Design Case Study, the Staple Fiber Cutting Experiment. So Doug has already introduced me, so I won't really spend time here except to say Doug and I are both Virginia Tech alums, so go Hokies.
You bet. I was going to wear my Virginia Tech socks in honor of that occasion, but I forgot them.
Very good. But I will say at Virginia Tech is where my love of statistics really blossomed. And I've been fortunate to work as a statistician at 2 companies, like Doug said, Eastman Chemical, and also now at Pfizer. And fortunately, both of these companies have great traditions of statistical excellence. And so it's been wonderful places to learn and grow. Before I get started, I also want to acknowledge my collaborators on this project. Dr. Peter Hoos is a professor at the University of Leuven in Belgium. And Peter is really the brains behind much of what I will discuss today. So it's been my immense privilege to work with him on this project. And I also want to acknowledge Ying Chen, who is one of Peter's graduate students, who has made significant contributions to this project as well, and I'm very thankful for that and for her kindness as well. So without further ado, let me describe the case study that is the subject of the experiment that we will discuss today. So like I said, I currently work at Pfizer, but prior to this position, I worked for 7 years at Eastman Chemical Company. And during my tenure at Eastman, I supported many projects in Eastman's fibers business. So Eastman produces cellulose acetate fiber in several different forms. And I don't know if you'll be able to see, I have some staple fiber here, which is the subject of our experiment today. And, it's cut up and it looks sort of like a cotton ball uh, in its raw form. But this cellulose acetate fiber is made from wood pulp and recycled plastic. So it's one of the many sustainable products that Eastman offers, and it's used in a variety of applications. So the fiber produced for today's experiment that we will discuss is primarily used in textiles, both in garments like shirts and also home textiles like bedding, and it's used in a few other applications as well. I brought some yarn, some craft yarn that I picked up at my local hobby store that's 100% acetate fiber. So it's kind of cool that the fiber made down the road at Eastman then showed up in yarn form at the store down the road as well. But this fiber is sold under the brand name Naya. The experiment that's the subject of our case study today is called the staple fiber cutting experiment. So this cellulose acetate fiber is extruded as a continuous filament fiber and crimped to add texture to the fiber. And then it's chopped up into this cotton ball-like fiber that I showed you. We sell, or Eastman sells, this chopped up fiber to yarn spinners that blend cellulose acetate fiber with other fibers like cotton or polyester, and make it into a spun yarn that's then used for applications like the textile applications I mentioned. But the experiment that is the subject of our experiment today, the part of that process is the cutting portion, cutting the fiber into these pieces. And so before the commercial launch of Naya staple fiber several years ago, Eastman purchased new equipment to cut up the fiber. Previously, this had been done externally, and they were bringing the cutting process in-house. And it's important that the fiber is cut to a specified length target with minimum variation around that target for successful downstream processing by Eastman's customers, the yarn spinners. And so the team I was part of wanted to study several factors in the staple fiber cutting process to determine their impact on the average fiber cut length. Since this process and the equipment were new, a statistically designed experiment provided a structured and methodical way for us to study and optimize this process. And the impact of this experiment is that by optimizing processing conditions, we provide good settings for successful customer sampling, production qualification, and commercialization. So that's sort of the background of this experiment. And now I'll dive into some of the more technical details. So this experiment studied 5 factors, and one of the factors was identified up front as a hard to change factor. And this factor is related to the material staging during the cutting process. And so resetting this factor would involve shutting down the process entirely, bringing in a change crew to make the necessary changes, and then starting the process again. So it's very obvious to us that this factor was hard to change. It would take a lot of time to change between different levels. And also this factor was categorical with 3 different levels. The other 4 factors in the initial design were treated as easy to change. All 4 of the other factors relate to equipment settings in the cutting process itself. And I've called the factors A, B, C, D, E for the purpose of our talk today. So factor B was a 2-level categorical factor. And then factors C, D, and E were all continuous factors. with the one added complication that factor C needed to have 3 levels. So this was a specific request from the 3 engineers working on this experiment with me. And so remember, this is new cutting equipment. And so the mid-level for this factor C was the recommended setting from the equipment manufacturer, but we didn't have any historical experience with the equipment and how it might operate with Nia staple fiber. And the engineers hypothesized that for this factor C, deviation from that midpoint, either on the high or the low side, could be detrimental to the process. And so they wanted to explore a space around that midpoint, but including the midpoint for factor C because of this hypothesized curvature. So you can see here that we have a main effect for factor C, and we also want to estimate this quadratic effect for factor C in our ultimate model. So before I discuss the design that I selected for this experiment, I'll spend a few minutes reviewing a few concepts related to the design that you may have covered in this course or that might be new to you. So first, I mentioned that one of the factors in the staple fiber cutting experiment was hard to change. And because of this, a completely randomized design would be difficult to execute. And so instead, we wanted to choose something called a split plot design. And a split plot design is characterized by 2 types of factors: hard to change factors, which are difficult to completely randomize. And for us, that's factor A, the categorical factor with 3 levels. And then also easy to change factors, where complete randomization is achievable. And for us, we have 4 easy to change factors. In a split plot design, experimental runs are arranged in groups to minimize the number of times the hard to change factors are reset during an experiment. So limitations involving time, material, cost, and equipment can make it inefficient, or even impossible to execute a completely randomized design. And a split plot design is a practical alternative. I'll give you a brief history lesson. The name split plot design originates in the agricultural industry. So agricultural scientists studying factors such as the type of fertilizer need to apply that fertilizer to a large section of land. And then in the same experiment, that scientist might also want to study different varieties of seed that could be randomly applied to subplots within the larger whole plot. So this is an example, an early example of a split plot design where fertilizer is the hard to change factor, and then the seed variety is an easy to change factor. So like I mentioned, for the staple fiber cutting experiment, we have 1 hard to change factor and then 4 easy to change factors. I'd also like to provide a brief overview of optimal designs. You may have run across these in the MOOC, but many designs that we first learn about when we learn about DOE are considered classical designs. So factorial designs and response surface designs are typically considered classical designs. But an optimal design is a computer-generated design where experimental runs are selected based on optimizing a specified criteria. 3 common optimality criteria are D, A, and I optimal. And optimal designs are flexible to accommodate many different scenarios, including things like a limited run budget, impossible factor combinations, or a complex underlying design model. So for the staple fiber cutting experiment, we have several complexities. So we have the hard to change factor, that's 3 levels and categorical. But we also have a little bit of a complex underlying design model. So recall that I mentioned we have an interest in that factor C quadratic term in particular, but we're not really interested in the quadratic terms for the other factors. So we don't need a full second order model necessarily. So all of these constraints and facts about this experiment led me to propose a design to the engineers on this team. And the design that I proposed was a weighted A-optimal split plot design with 36 runs. So I have the design here on the slide, and you can see the hard to change factor is factor A. And the 36 runs in the experiment are divided into 6 groups of size 6, so that factor A is only changed 6 times throughout the experiment. So you see I've color-coded the groups here. So there are 6 groups with each level of factor A repeated 2 times. So that's about the split plot part of the design. The other part, the weighted A-optimal part, the reason I chose this type of optimal design goes back to the comments I've made about factor C, the continuous factor with 3 levels. Since the engineers were so interested in that C-squared quadratic term, I wanted to make sure that we could estimate this term and that the design had sufficient power for determining whether or not it was significant. So I turned to an optimal design, and specifically a weighted A optimal design, which gave me the flexibility to place additional weight or importance on this quadratic term so that the computer would generate a design for me that included sufficient runs at this midpoint, this 0 level of factor C, for estimating and testing this quadratic term. So I ended up selecting a 10 times weight on this C-squared term, and that produced this design that is actually balanced across the 3 levels for factor C. So there are 12 runs each at the low, mid, and high level of factor C. Now, I don't actually use this weighted A optimality criterion very often when I'm designing experiments. I find it rare that we have information a priori about a hypothesis about an individual term that we want to have, greater precision to estimate. But this seemed like a good use case to me that I came across in my work at Eastman. Now, the experiment was also completed over 2 days, although I did not design the experiment with a block term because we did not expect there to be much of a difference between the 2 days. And so this is the experiment, this weighted A-optimal split plot design. This is the experiment that I proposed and that we started with. But you might be wondering, how did we get from this split plot design to the design I referenced in the title of this presentation, a staggered level design? Well, it doesn't matter what plan you have, there always seems to be some kind of hiccup or problem that you encounter in the real world. So on the day of the experiment, before the experiment began, it became abundantly clear to us that this factor B was also going to be hard to change. Remember, factor B is a 2-level categorical factor. And factor B involves changing out a piece of equipment. And since we didn't have a lot of previous experience with this cutting equipment, we didn't realize until we really got down to conducting the experiment how much time it was going to take to change out factor B. It's more labor intensive than we realized. So that led to an emergency solution. The 36 runs of the weighted A-optimal split plot design were reordered to reduce the number of changes for factor B. So that reordering produced this experiment on the slide where factor B is reset fewer times throughout the experiment. But it's also reset at different time points than when factor A is reset. So you see there are 8 groups for factor B here, and these groups are either of size 3 or size 6. And so notice how the change points for factor B don't align with the change points for factor A. Because even though factor B is hard to change, it's sort of less hard to change than factor A for this process. And so I have to admit, initially I was quite worried about this emergency solution and analyzing the results of this experiment and if we were going to be able to learn anything or draw strong conclusions. But the structure here was very intriguing to me, and somehow in the recesses of my mind, I remembered something. And that was several years ago, I had attended a short course at a conference presented by Dr. Hoss on split plot designs. And during that course, Peter had made a brief mention to staggered level designs, including some work that he had published several years prior. So I looked up my notes from Peter's short course and found the papers that he referenced, and I reread the papers, and that made me quite sure that this staple fiber cutting experiment would be categorized as a staggered level design. So I reached out to Peter and asked him about my experiment, and thankfully Peter is quite kind and quite collaborative, like Doug is himself. And he replied quickly and offered to help me study this design and complete the analysis successfully. And I'm so glad he did, because it's been a wonderful journey. So back to the staple fiber cutting experiment. I've already mentioned one surprise from this experiment, the fact that factor B was hard to change, which is not something we originally planned for. But there was a second surprise that is sort of a good surprise. And that surprise is the fact that factor A could really be treated as quantitative rather than categorical, as I had originally incorporated it into the design. And that's really sort of my fault, something I probably should have realized sooner in the process. The 3 levels for factor A represent 3 different configurations for the fiber being cut. And so in my mind, they really seemed like 3 distinct categories. But really, once I got deep into this experiment, I realized that we could think about factor A in terms of the amount of material being cut, a small amount, a medium amount, or a large amount. And in this way, we could treat factor A as a continuous factor, which ended up being quite helpful in the analysis. So those are the 2 surprises that contrast with how we set up the design. And at this point in my discussions with Peter, one question that I had was, could we have done better? Is there a better design that could have been selected if I had known about these surprises up front? Because now the weighted A-optimal split plot design that I selected is no longer optimal given the change in scenarios. So could we design something better? Of course, the experiment is already completed at this point. This is a hypothetical to help both myself grow as a practitioner, but also other statisticians in industry to learn from this example. And so this is where the wonderful Ying Chen came in, Peter's graduate student, and she came on board and she wrote a program that would generate optimal staggered level designs using MATLAB so that we could answer this question, is there a better design out there than what was actually executed? So Ying generated D, A, weighted A, and I optimal staggered level designs for the staple fiber cutting experiment, the actual scenario that ended up occurring. And what we did is we compared these optimal designs to the Eastman design, which is what we will call the design that was executed in reality. The good news is that the good news is that the Eastman design is pretty good relative to these optimal staggered level designs. And I'll prove that to you in the next few slides. But a better design could have been generated if we had known all these constraints up front. So let's see. These plots illustrate the structure of each of the optimal staggered level designs that Ying generated. And the Eastman design was balanced across every level of the 5 factors, similar to what we see here in the A-optimal design. And that balance was really sort of my doing, just my preference for wanting to have balance in the design that I originally selected. But you can see the D-optimal staggered level design would have included fewer runs at the midpoints for factors A and factor C. And interestingly, the weighted A and I optimal staggered level designs also include a few runs at the midpoints for factors D and E, even though the design model does not specify a quadratic term for these factors. So that's an interesting occurrence related to the design generation algorithms. Here I have, this is the Eastman design for comparison, like I said, similar to that A optimal structure in terms of balance across all of the factors. And now this table summarizes the efficiency of these optimal staggered level designs relative to the Eastman design. So how you interpret this table is that if the efficiency is greater than 100%, then the optimal design, the optimal staggered level design that Ying generated outperformed the Eastman design relative to the evaluation criteria, D, A, weighted A, or I. So overall, you see a lot of the numbers in this table are certainly greater than 100%. So overall, the optimal staggered level designs did outperform the design, the Eastman design as executed. But two caveats. One, the Eastman design was still pretty good. So we're talking about efficiency gains of less than 10%. So that made me feel good that the design as executed was still pretty good, even given the changing scenario that we had to deal with. The second caveat is that currently there's no easy way to generate optimal staggered level designs. So Ying wrote a custom MATLAB program to generate these designs for this comparison, but standard software packages don't offer staggered level designs yet. So that's something that would be a barrier for many practitioners in industry. So that's a little bit of a comparison about sort of the structure of the Eastman design and what other types of designs could have been generated if we had known all the information up front. The final topic I'll discuss about this experiment is the data analysis. What did we learn from the experiment and what were we able to conclude? So I conducted backward model selection based on p-values to determine the significant terms for the empirical model based on the results of this experiment. Like I said, I didn't design the experiment with a block term, but I did investigate whether we should have included one, but there was no significant day-to-day variation. In the model, the significant effects included all of the main effects except for one. Factor D was not significant. 3 significant interactions, and then in particular, no quadratic effects. So remember, the engineers were just so interested in that C-squared effect, and we took such special care to design the experiment to study this potential curvature, and then it did not end up being important for the system. But the good news here is that because we took that special care, we feel confident in this conclusion and sort of disproving their hypothesis concretely. We do see some substantial correlation due to not resetting the hard to change factors. We see that in the estimated variance components that's listed here. Here I show a diagnostic plot showing the actual observed fiber cut length results versus the model predicted cut length results. You see we have an R-squared value that's quite high at 98%. Demonstrating that the model was quite a good fit to the data, so we did have some robust conclusions from this experiment. And then here is a visualization of the empirical model using a prediction profiler. So you see no curvature with this factor C. It's a linear effect relating factor C to the mean fiber cut length. And the modeling analysis did allow us indication of how to optimize processing settings for the mean fiber cut length, which was the entire objective of the experiment. So in particular, one major learning was to understand that the hard to change factors, factor A and B, remember factor A was our original hard to change factor, and then factor B was our surprise hard to change factor. But these two factors could be fixed at a level, convenient for the process or for the engineers, and different cut length targets could be achieved by varying just factors C and E. Now you can see there's a large effect for factor B, and so we cannot achieve all targets just by varying the easy to change factors. But there is some wiggle room, some ability to hit different targets by fixing the hard to change factor. And before this experiment, the hypothesis was that this effect for factor B would be so large that there would be no overlap between sort of the low level and the high level for factor B. But that proved not to be true. So that was an important learning and also a significant learning for how this process could be run in daily production. So in conclusion, what we've learned about today, the staple fiber cutting experiment is an example of how runs are sometimes reordered due to the hard to change nature of certain factors. Ideally, we do not reorder or re-randomize the runs in an experiment, because that randomization is important for executing a designed experiment. But sometimes practical constraints get in the way, and we have to think creatively to find a suitable solution. So the resulting design here is called a staggered level design. If all the information concerning the nature of the factors, for example, the hard to change nature of factor B, had been available in the planning stages of this experiment, a 5 to 10% efficiency gain would have been possible. And this is equivalent to wasting 2 of the 36 runs. So while not a large gain in efficiency, in the real world, experiments cost time and money. And so every gain is important. The good news, like I said, is that the emergency staggered level design did allow for optimal processing conditions to be identified, and that information is used to inform the current fiber cutting production process at Eastman. So I'll just wrap up by again acknowledging the work of Ying Chen, who was integral to this work and to comparing the Eastman design to optimal staggered level designs. And I would be quite remiss if I also did not acknowledge the work of the 3 development engineers whose dedication to planning and collecting rigorous experimental data enabled this novel experiment. So I'd like to thank Kevin Barham, Jessica Rimmert, and Yubin Shin. It was a pleasure to work with the 3 of them while I was at Eastman. And with that, that is my talk for today, and I'll hand the mic back over to you, Doug.
Katie, thank you very much. This was really, I think, a fascinating talk. And a couple of things emerge from this that are really quite interesting. Redesigning the experiment on the fly, and I'm assuming that when these discoveries were made about more hard to change factors, that you were on site, okay, and so you were able to get right in the middle of that and make what seemed to be really good decisions.
Well, yeah. So, Doug, I will say I misled you a little bit because while I was at Eastman, I did often sort of participate hands-on in experiments. And I had worked closely with these 3 engineers several times before, but I really owe a lot of credit and admiration to these three because I was on my honeymoon while they were conducting this experiment. So was, out of pocket, so to speak, not answering questions. And so these engineers, sort of based on the knowledge that they had about designed experiments, made the redesign choices themselves, which I think is actually quite impressive to come up with the design that they came up with. On the fly, sort of without me present as I often was.
I'm amazed because they obviously have a lot of insight that I wouldn't necessarily expect them to have. That's great.
Yeah, quite advanced.
I'll tell you a horror story from my own experience. Okay, where it didn't work out that way. When I was a faculty member at Georgia Tech, I did a lot of experimental design consulting for various other units around the campus. And one of the groups that I worked with from time to time was in the College of Architecture. There was a couple of faculty members there that were interested in building design features to make it easier for visually handicapped people to navigate around the building. And so they were always, testing things like floor surfaces, floor materials, things that they could add to walls, things that would provide information about what kind of opening are you approaching? Is it a door to a room? Is it a door to a bathroom? Is it a hall? Or is it a flight of steps? Those sorts of things. And it was really fascinating to design some of these experiments because they actually had to build these structures. And then they had a group of visually handicapped people that would serve as subjects, and they would come in and they would navigate this and collect data about how successful they were in doing that. So we set up one of these experiments and designed it, and they were going to run it over a period of about a week. Sadly, it was the week of the FTC.
So you were out of pocket.
So I left town to go to the FTC. And so they started running this thing. And some of the factors turned out to be way harder, way harder to change than they had found that they had thought. And so they just made some arbitrary decisions about re-randomizing all of the runs. And so fortunately, it all seemed to make sense when we analyzed the data. So maybe what they didn't hurt, but I was really horrified when I got back and saw what they did, and because I was so adamant about getting it run the way we designed it, and the way it ended up was not even close. So you have some really good colleagues to congratulate for doing a great job with that. And the other thing that I wanted to ask is why did she write the code in MATLAB? If she'd written JumpScript, you could make that JumpScript available and people could use it as an add-in. You could stick it right on the toolbar in Jump. So
yeah. That would be a great idea. Maybe that's an avenue for future work. So Ying had done her master's thesis, writing a MATLAB program to generate optimal staggered level optimal designs, and then she modified it for us for this application. So I think it had to do with her prior. But I agree. We should think about a Jump add-in.
Well, as I understand it, and I'm speaking from a position of ignorance here because I am not a coder. Okay, but I have had some graduate students that are very good coders, and they tell me that there's not a lot of difference between MATLAB and the Jump scripting language. That if you have code in one, you can easily convert it to code in the other. And now I'm saying this, from a position of ignorance, but I'm relying on one of my former PhD students who is a brilliant coder. I mean, absolutely brilliant. This guy, he knows everything about every programming language on the planet, and which he needed in his dissertation. So because he had to do a lot of coding. But so maybe that's something to think about, because I think this is a very valuable tool. I think what you've done here is extremely, extremely useful.
Yeah, I agree, and certainly something to explore, because it certainly is a very high barrier, a very steep barrier, if there's no easy way to generate this type of design. If
Yeah.
you're just relying on trying to reorder the runs yourself, that's not recommended. Like Doug said, I too have had many horror stories where the runs and experiments were re-randomized, and then I cry tears of sadness about the information that was lost, and the difficulties that we will have during the analysis. So it's not always a happy ending,
Well,
like we talked about today.
When I teach my course on experimental design here at ASU, I take them through that 7-step process in the first chapter of my book on how to successfully plan and conduct experiments. And I always tell them that we get down to the next to last step is executing the experiment. And I say, most important thing is, if you want it run right, either do it yourself, okay, or be there and watch every single thing that they do.
That happens.
Because if they don't decide to reorder the runs, sometimes they will forget to reset some of the factors. They know that they need to turn this knob from setting 1 to setting 2, but they forget to do it. And blows everything up. So I think your guys did a remarkable job. You should really
did
pat them on the back for doing a really, really clever job. So
they really did.
Yeah, that's really great. And if you write this thing up as a case study, that would be something to really emphasize, I think.
Yep. We are in the process of submitting a paper for publication, in the works. So
good. Excellent.
We're working on that. Again, Peter and Ying, for that matter, are really the brains behind that. I just provide the industry example.
Well, I'm glad they're going to do that, because it's going to be informative. So let's see. We've got some questions, I think, in the queue here. Okay, Katie, can you see this one? Or not? Wait, we're working on making it possible for you. I think you can see it now.
She would have to open the Google Doc on her own.
Oh, that may be complicated. That's okay. I can.
I say, if you want to dictate,
let me
easier.
Let me read it. It says, I'm currently an engineer at a lead metallurgical plant for lead acid batteries. And I'm trying to solve a problem with 7 factors, including continuous and categorical factors, involving 2 major factory processes, refining and casting. I understand that the experimental unit of my test is relatively large, which causes the logistical cost of running the experiment to increase. Due to these difficulties and lack of support from management, I needed to reduce the number of variables to just 3, and I'm blocking one of them. I would really appreciate it if you could share your non-statistical knowledge on how to conduct an experiment in an environment where no one knows the DOE methodology in depth, and how I can better sell the benefits to stakeholders. I'm sorry. Really an interesting question, kind of a dilemma. What do you, how do you go about doing this? I've had some experience in doing this. I've done a lot of consulting work, and very often I'm brought in as the consultant because there's really no one in the company except maybe 1 or 2 people that know anything about experimental design, and they know that they need to do it. they want me to sort of, be the DOE expert. And one of the things that I've done in sort of trying to help people do this is to have some very short, like 1 hour meetings with people, including the management people, and try to give them an explanation as to what this is all about, and maybe a couple of examples of what the benefits are, to get some awareness of the concept. That's always helped me, but that takes some time. If this is really a hot problem, then you're probably going to have to do some of this one-on-one kind of salesmanship, working with people. But it is difficult to get organizations started down this road. And typically, I had the best luck when I was able to start sort of at the management level, and explain to them what this is all about and why this could be really beneficial to you. Do you have any thoughts on that you'd like to share with our viewer here?
Sure. I think one piece of practical advice I might give, maybe it depends some on the climate, but it sounds like, there's not, at your situation, there's not a lot of, understanding or maybe even support for a DOE approach. And so a practical piece of advice I might give you is to start small. I mean, it's, I have quite a lot of experience designing, conducting, analyzing experiments, and there's always something that sort of goes wrong, and sometimes it's something small that we can deal with, and then other times it's bigger things in this, like in this example. But that's just life. I mean, that's just the real world. There's always complications that we have to deal with. And so if you're trying to sell sort of a new approach, you want to sort of make that first try as successful as possible.
Yep.
And so, on the one hand, DOE is able to tackle complex problems, multi-factor experiments, lots of complexity. But on the other hand, how do you eat an elephant one bite at a time? So, sort of maybe think about what's that first step where you could demonstrate the power of a statistically designed experiment without sort of getting in over your head, because you might only have, one shot to really make that impression.
That's right. Don't try to invent the atomic bomb with your first experiment. Just get something to blow up.
Yeah. Just show that you can learn something.
Yeah.
And then maybe you'll get a little bit of buy-in, and like Doug said, there's lots of examples, industry examples in papers, online, that you might be able to find another company in your industry who's applied DOE to help. There's nothing like showing what the competition is doing to spur your management to action.
And actually, the MOOC may help you.
Yeah.
The MOOC is out there, it's available, and you may be able to say, here's some pieces of this that you ought to go look at, and maybe that would help. But yeah, the getting started thing is always a bit of a challenge. It's always a bit of a challenge.
Wish you luck.
Yep. Oh, how do we determine the best response surface design? Well, here's what I would say is take the MOOC. Because
learn from the expert.
we have a whole course within the MOOC on response surface methods, and so but I mean, it is a good question, and it all boils down to, again, what are your objectives? What are you trying to do? Are you trying to screen factors and then optimize, or do you think you already know what all the active factors are? What's the objective? Is the objective prediction? Are there multiple responses? Do the responses have different distributions? I mean, there's a the whole host of things to think about, and there isn't one simple answer to that question. Your thoughts, Katie?
Yeah, two things come to mind. First is when I work with teams, I always encourage them, like you said, Doug, to write out in words, what are we trying to accomplish with this experiment? What do we want to learn? What's the objective?
Mm-hmm.
And I so often find when teams write it out in words, sometimes that ends up being the entire meeting is, wait a minute, I thought we were doing this. I wanted to learn this. And but aligning on this is the objective for this experiment will help select the proper experiment to accomplish that objective. And then the second thing, oh, go ahead, Doug.
I couldn't agree more. The 7-step process that I recommend that people go through, the very first step is, what is the problem we're trying to solve? And that typically involves a meeting of people from different backgrounds. It's the process people, it's maybe even the maintenance people, it's somebody from QA, maybe somebody that interfaces with the end user, the customer of this price. So yeah, you get all these people together in a room, and sometimes you find out the problem isn't what they thought it was. It's something different. And getting a good statement of what the problem is goes a long way toward answering this question. Very good point. Very good.
Yeah. For sure. I was also going to say, when I teach DOE, I usually emphasize there is no right design or perfect design for a problem. There's different designs with pros and cons. So what would you learn if you conducted a larger design versus a smaller design? What's the practical cost, to your company or to your situation?
And what are the constraints? Those are all
right.
things that enter into the answer. Yeah. This is back to the. Okay, this is more of the lead refining process. Wants to study 3 main factors and facing a great execution challenge due to the complexity of the environment and the difficulty of changing one of the factors. The 3 factors are pump speed, lead level in the reactor, and casting tube temperatures. And one of the main complexities outside of logistical complexities is the inverse relationship between 2 of the variables. Add to this the fact that I can't really control the lead level in the reactor. The only thing I can do is wait for the level to drop naturally as a result of the flow to the ingot mold, and use the short event time between when the level reaches the highest specified level and after that in the lowest level. Try to create a split plot using custom design and jump, where the lead level is a hard to change factor, but I always get a low power value for all the main effects of interactions, even with 30 plus runs. And due to the inverse nature of speed and level, where the lead level of the reactor drops, the operator is automatically forced to increase pump speed to maintain mold filling. Suspect there's a nonlinear behavior of the lead speed bomb and a possible interaction. People at the company where I work cannot believe that it is possible to obtain results through planned experiments, but this is mainly due to a lack of knowledge of the subject and statistical training. The only thing I can think of is to try to create a central composite design, but I can't do all the runs on the same day, which creates another problem. Well, a couple of things that I might suggest. Maybe this level problem is maybe the way you treat that is as a covariate. You can measure it, but you can't control it. So you try to design an experiment where you can control the other factors, and then either during the run or at the end of the run, at the beginning of the run, you measure this lead level and treat it as a covariate. I mean, that's what we often do when we have factors that we can't control very easily, but that we can at least measure. So that's a thought. Maybe that's another way to think about going about this problem. Katie, you have any thoughts on that?
I had the same thought, Doug, that that factor sounded like it could be treated as a covariate.
Yeah.
And then the other comment about low power for the hard to change factor, that's a fact
Yeah,
about split plot designs, that you'll have lower power for your hard to change factor because you have less changes in the
right.
design.
That's right.
So
And
it's
in effect,
the
what it does
expected.
is it reduces the number of levels of the factor. So you get lower power. It's just unless you run a lot of whole plots.
Yeah, which sort of, defeats the purpose of saving resources, so to speak.
Right.
So that's just going to be a fact of the design.
Yeah, it is. And so here's a question for you. Could you please show an example of the staple diagram you obtained?
I'm not sure I know exactly what that means. I don't know. Let's see, of the staple diagram, you think this means of the model, Doug, or
That's what I would think. But I don't know. I'm sort of like you, I'm a little unsure.
see. I guess I don't know if we can just ask for clarification. I'm happy to pull up the screenshot of the profiler if that's what the question is referring to.
Well, that would be the my best guess.
Yeah, I'll just share that real quick since
Okay.
I can pull it up now.
Yeah.
Let's
Yeah.
see.
Mhm.
You seen the profiler? So
Yeah. Mhm.
it's what we discussed, a few minutes ago. So a visualization of the empirical model for the staple fiber cutting experiment. This is obviously, if you're not familiar, this is using JUMP, the prediction profiler platform, which is really nice. And this is a screenshot, but in JUMP, it's interactive so that
Right.
you can see what happens when you change different factors, because there are some interactions behind the scenes that are present in this model. Yeah.
But
so
the profiler accounts for that when you make
correct.
adjustments. Yeah.
Right. So the interactive profiler will account for those interactions, but this, screenshot version, I did not display the interaction plots here.
Right. But if you adjust those sliders, the curves respond to the interactions if there are interactions present. So you get the right interpretation.
Yeah. It looks like this person put in the chat a clarification. I was thinking statistically, but the colleague mentions a staple diagram, which would have to do with how the mean length is measured. And this data is all masked. It's not the actual data that we used. I'm not able to disclose any actual data due to confidentiality.
This proprietary information. Sure.
Yeah. So I can't share any of that, unfortunately.
Fascinating experiment. And how well it came out. Despite the complications.
Right. Like we said earlier, it's not always a happy ending,
Yeah, but this was great.
Yeah.
And by the way, we are out of time.
Oh, very good. Yes.
And I want to thank you so much for taking time out of your day to do this. End of today's questions. We are going to have another fireside chat in October. We don't have the date pinned down quite yet, but that'll be posted pretty soon. And you can find past recordings in the resources tab. And looking forward to having everybody back next month. And Katie, once again, thank you so much for doing this. It's just a fascinating talk.
Thank you so much, Doug. It's great to be here.